Okay, well, welcome back. Today is February the 25th. We are one lecture behind, but that's usually not a problem. Typically we're ahead at this time, but the tests are slowing us down slightly. That's all right. So today, well, your assignment 2 should be in. Tutorial 4 is due this weekend. It's listed as Saturday, but I will probably leave it open all weekend. Until like Monday morning, right? So till here, 8 a.m.-ish. um, so yeah, it's just linked lists, which we took last class. I'm going to do one more bit of linked lists before we jump into inheritance. I'm going to do the remove function. I'm just going to do it really quickly and highlight a couple things, but yeah, that's where we stand. Any questions? Okay. Um, so we talked about singly linked lists, and we had implemented an add function, and we looked at all the different cases that we had to consider for that. I'm going to very quickly go over the remove function. I guess not as quick as I thought. We will need these slides, or at least part of it. We didn't quite get to remove, and I think there's some important things to highlight. And also, that could be a hint, the fact that I do want to do the remove. And we have a test coming up that I said linked lists would be on, so it might be a good idea to know it. But let's talk about just the general case of remove, and then we'll look at all the special cases. The general case of remove is this one. I call, say, remove B. And then, of course, I'm going to do a traversal. I have my previous and my current pointers. Previous is pointing to null or nothing at the moment, and current is pointing here. And then I say, well, is B equal to current? Is this the thing we're looking for that we're trying to remove? The answer is no. So I'm going to update previous to point to current, and current to point to current dot next. And then I'm going to say, well, is current equal to the thing that I'm looking for, equal to B? And in this case, the answer is yes. All right, so then I want to remove this node from the list. And how I want to do that is, well, if I'm traversing the list from here, I do not want to go to that node. I actually want to go to the next node in the list. And so the piece of code that allows us to do that is quite simple. It's previous next equals current next. And really, that's it, right? So this node that current is pointing to still points to this other node, but I don't care about that. I'm going to be deleting this node, so just this one line is what I need to remove that node. And then I'm going to, of course, store the student, delete the node, return the student. And then we'll deal with the other sort of special cases like removing from the front or removing from an empty list. This should go very quickly. Oops. All right, so yeah, right now we add a bunch of students at different places and then print them out. And now I want to start trying to remove some. Well, the first thing I can do is check to see if my list is empty. So if head is equal to null pointer, well, then I don't need to do anything. I'm going to return null pointer, and that's done. So now I can assume that head is pointing to something useful. I'm going to make a current node that points to head and a previous that points to null pointer, the same as before. I want to do a traversal the same as before. So while current is not equal to null pointer, And then I'm going to do some work, and then after that I'm going to walk forward. So previous equals current, current equals current, next. And well, the thing that I want to do is I want to check to see if current, the data in my current node is equal to the name. So if current data, and that returns a pointer to a student object, and student has this getName function, I believe. In fact, I'm almost 100% sure, although it's not auto-completing for me, but I believe that will work. So on a test, right, what you want to do at this point is check the student class. And so I can use equals, and it says, well, if the name is equal, then this student is equal to that. Or I can use the getName function. Either of those are viable options. But make sure you check, right? I do see people, trying to maybe game the system a little bit and look at past tests and try to memorize the questions that I asked on past tests. And so then they give me a function that doesn't actually exist. Well, you're going to lose marks for doing that. So do be careful of that. All right, so if this is true, then I found the one I want to remove. So I'm just going to break as usual. Once I'm here, well, the piece of code we said was previous, next, equals current, next. And then, I want to store my student. I want to delete current, right? Good memory management, and then return goner. Okay, so if we look at the diagram, that this is previous next equals current next is this arrow here. Then I can delete this node, and then this student, I've stored it, so I can return it. All right, so let's see if that works. So up to here, we've added students. I guess we're gonna add a few more students just for fun. All right, print them out, and then down here we'll start removing them, starting with Bob. Now Bob doesn't exist, so let's consider what that means. But let's look at the code. I do have stu is a student pointer. And so I sort of, whatever is returned by this gets put in my student pointer. So when I try to look for Bob, basically stu should be equal to null pointer. So I'm going to skip all this and just go here. That's what should happen. Let's run it, see if it does. Of course not. It's a seg fault. Okay, so what happened? Well, we ran off the end of the list, right? We kept looking for Bob. Basically, if we go back, I have a clean version. Yeah. So if I go back here, let's say I said remove D. D, not B. Well, of course, it never finds D. So it ends when current is pointing to here and previous is pointing to here. Well, current is pointing to null pointer, which means that probably this piece of code down here that I did, right? This is not going to work because here I'm trying to dereference a null pointer. So again, I'm just going to be really explicit about it. I'm not going to try and be clever or elegant. I'm just going to say, well, if current is equal to null pointer, then I didn't find what I'm looking for, right? It means I went through this entire while loop and I exited when current went off the end of the list. So I'm just going to return null pointer. And whoever called is in charge of checking to make sure that that's what got returned. I don't need to do anything else. Otherwise, I can do this and then delete all this stuff. So now Bob, the search for Bob should be unsuccessful but not crash, which it did. All right, so let's remove somebody that actually exists. Tony exists. Tony exists in the middle of the list. So again, if stu is not equal to null pointer, that means we have something. We're going to print that student out, and then we're going to delete that student, because if we don't, then right, it's certainly not going to get deleted in the linked list now. So. All right, so removing Tony, we did find a student named Tony. That's what they printed out. When we reprinted out the list, Tony doesn't exist in it anymore. And the list still seems like well-formed. There's no weird, weirdness going on there. All right, so that seems to work. Let's remove the last person in the list. Is it Zeke? Let's remove everybody, and then it might crash. Right? Well, actually, we can even anticipate it, because it's going to do the same. It's going to crash in the same place that it crashed on the add. That's when we remove the first thing from the list, because we didn't handle that case, right? If we do that, then we have to reassign the head somewhere. So to remove the first thing from the list, where is it? It's here. And so we have previous equals null. We have current is pointing to here. We call remove A. We say, in the while loop, the first thing we do is say, is this equal to A? And the answer is yes. So when we exit, previous is equal to null, and current is pointing to the thing we want removed. So yeah, let's do that. So if current equals null pointer, we return that. So we know that current is not equal to null pointer, but we can say if previous is now equal to null pointer, well, this is removing from the head. Well, then I want to do head equals head next. And then I can do this, this part. Or I'm going to be slightly clever, not really, but. All right, so if I get past here, that means current is pointing to something, which is good. If previous is pointing to nothing, that means current is pointing to the head, and we have to do this. We have to advance the head, but current is still pointing to the thing we want removed, so that's fine. Otherwise, we have to do this step to remove current from the list. All right, well, let's see if it works. Seg fault. Okay, no, it did not work. Removing Amy. Previous equals null pointer. You know why? Because I didn't save it. Let's try that again. Printing empty list. There we go. It worked. Everyone got removed from the list. Printing the empty list did nothing. I run this with Valgrind. No memory leaks either. All right, so very good. Of course, the one thing you have to watch out for is if we did something like well, get the honor list, right? So something like this, void get honor roll. Right, if we implemented this, then this is an output parameter, right? So inside here, I would just iterate over everybody in the list. And if they were on the honor roll, then I'm going to add them to this other list. If I'm only adding pointers, then that is going to cause a problem up here with my memory management, right? Because now I'm deleting data, but I might have some students that are in two different lists, and so they're going to get deleted twice. And if I don't delete them twice, then I have a memory leak. So one way or the other, this is going to cause problems. But yeah, questions? All right, so yeah, I did want to go over remove. I mentioned that I might. Again, you can break it down into explicit steps. That's okay. Something like this might appear on your test. Questions? Okay. All right, so that takes us to the end of linked lists. We already did the woo clap, so we're going to start on inheritance. So inheritance is, of course, one of the pillars of object-oriented programming, at least the way object-oriented programming evolved, right? So we're going to talk about it. We're going to look a little at, because it always kind of bugged me a little bit that when I learned programming, it was different, right? Now you have like all these high-level languages and paradigms and stuff. When I learned, things were quite low level. So we learned on something like, well, Pascal, which was a lot like C, I guess. Which is pretty transparent as to what your hardware was doing. And then later we learned object-oriented programming, and when we learned that, they said, well, don't worry about what your hardware is doing anymore. Just like here's this brand new magic thing that magically somehow runs on your computer. And I didn't like that lack of transparency. So we're just going to look a little bit at, we're going to peel back the curtain a little bit. And so we'll look at memory layout and like what is your hardware actually doing when I have an object inherit from another object. All right, and then we'll look at, of course, access because, well, C++ things are encapsulated, things can be private, and what does that mean in terms of inheritance? Constructors and destructors, member functions, types of inheritance, multiple inheritance. We'll talk about all these things. So the role of inheritance in object-oriented design, it's in some sense another method of abstraction, encapsulation, code reuse. In fact, what we're going to see though is it's a lot like composition, basically. We'll see how exactly it's like composition. But when we talk about inheritance, we are talking about an is-a relationship, right? So if, well, on your assignment, you have, what do you have, a lab tech that inherits from entity. So in lab tech is a entity, right? So it's a way to help reuse existing code. In C++, the terminology is often base class and derived class, but we also might talk about parent class and child class and any other sort of thing like that. Well, let's consider what might happen in C if we wanted to, we have a boat, right? And it has some features, some properties. And then we want to make a sailboat. Okay, well, a sailboat is, we want to have the features of the boat, right? So one thing we could do is just include an instance of the boat in the sailboat struct. And then we might add some other features, right? And if you looked in memory, it would look something like this, right? My boat just looks like this. It's composed of an int. My sailboat, well, the first part of the sailboat is actually a boat, right? So the first 4 bytes are just a boat. And then the other 8 bytes are the member variables of the sailboat. And so that's how I might solve that problem in C. And actually in C++, it does exactly the same thing, right? So inheritance, if I instead do this, so now I have a boat, and yeah, maybe I have a function, but that's not going to affect the data. And then I have a sailboat, and the sailboat inherits from boat, right? So this is how we inherit in C++. We will go over that in detail. So our boat is the base class. Our sailboat is the derived class, so it inherits from boat. When we look at the memory, it looks exactly the same as when we used composition, right? So that model of like inheritance is really kind of composition. That's very useful in terms of, it'll be useful in terms of like, how do I solve problems with inheritance and what, sort of thing should I consider in inheritance? Well, just think that when you get right down to it, it's just composition, right? Now there's going to be some stuff that the compiler enforces, but at the end of the day, this is a useful way to think of it. Of course, like composition in C++, we have to consider access, right? Just because Just because a boat might belong to a sailboat doesn't mean the sailboat gets to access the private members of boat. And it's the same thing with inheritance, right? Capacity is private to boat, which means that my sailboat cannot directly reference it, as we will see. The exception is protected, well, public, of course, everybody can access. But protected relates directly to inheritance, so that means my sailboat can access any protected members of the boat. And so let's look at what some of the consequences of that are. Oops. All right, so I have an animal class and I have a chicken class. This is my animal class. My animals have a name, they have an age, and they have a lifespan. Name and age are private. Lifespan is protected. I have a getter here and a print. And I have some default values. And then, well, the implementation doesn't do much, but it tells us when we're in the constructor, when we're in the destructor, and then it prints for us. So let's... Yes, of course. All right, so we made an animal called Alex. The constructor was called, we printed out Alex. Alex, age 8 with a lifespan of 12, and then Alex was destroyed. All right, so now in our chicken class, we want to inherit from animals. So how we do that? Well, we make a chicken class. We've included animal.h, of course, because the compiler needs to know what an animal is. And previously, when we make a chicken class, it looks something like this. But now we're going to add a colon here, and we're going to put, and it's important to remember the public part, because in C++, there's different types of inheritance, and public is the one that we traditionally think of. So public inheritance from animal. All right. Well, technically now, I should be able to do something like, let's get rid of Alex. Right. So I haven't really done anything, but chicken is going to inherit all of animal's members. So I should get a print. And I do, right? So, but now I got default values. I got a default value for the name. Well, what can I do something like this? All right, so animal, technically, all of these have default values, so I can just supply the name to an animal. If I try to do that to a chicken, of course, the compiler doesn't like that. So I inherit everything. I kind of inherit the constructor, but I'm not allowed to call it directly, right? So I have to make my own constructor for the chicken class. So let's do that. Typically, what I would do is I need enough information to initialize the animal part of my chicken, plus whatever extra chicken stuff there is, all right? So I need all of these members. I need this to be public. And I'm going to add int egg count equals 0. I'm going to add something called egg count, which is a member of my chicken class. How many chickens or how many eggs they lay per day. All right. So now here, age, oops. Load lifespan and int egg counts. All right, so well, I'm going to egg count equals EC. I can definitely do that, right? Because egg count belongs to my chicken class. But this name presents a problem. Now let's try and compile that. All right. Oh, yes, I do need a chicken. For some reason, why would I do that? All right, so yes, I also have to add chicken to the make file because I am not compiling chicken here, so. All right. Okay. So, well, the problem is that name is private, right? So name belongs to my animal class and it is private. And in my chicken class, I tried to access it directly, but I'm not allowed, even though I inherited from, um, this animal class. I don't have direct access to name and I can't set it. Lifespan, I can because lifespan is protected, right? So, well, this should compile now. Good. My animal constructor gets called here. Let's add. So we can see when it's getting called. All right, so animal gets called, the animal constructor gets called, then the chicken constructor gets called. And then I print out my chicken, but I use the animal print. So I have two problems here. One, not everything is being initialized. And two, I want to print out some extra chicken stuff because my egg count's not getting printed. Right, so I'm going to add here a print function. And I'm also going to add a destructor. And I'm not going to do anything special in the constructor other than announce, or the destructor other than announce that my chicken is being destroyed. And then void. Okay, well, again, I'm faced with the same problem in that I want to print out, I still want to print out my animal parts, but I want to add some chicken parts to it. But I don't have direct access to these animal members. But if I consider back to what I did in composition to solve this, right, when we had a student that contained an address, well, I just used the address print. So I'm going to do the same thing here. My animal has a print, and so my chicken, in some sense, has an animal part. And so I'm just going to call on that animal print function. But how I do that now is, well, I don't have an animal member, so I don't use the name of the variable, but I can access my animal parts using the scope resolution operator. All right, so an animal is part of this chicken class, and to access those animal parts directly, right, if I just called print, it's going to call this print again. So if I want the animal print, I just have to specify using the scope resolution operator. And then I could say, and is a chicken who lays egg count per day. All right, so when I said it's useful to think of it as composition, it's because we solve the problems, the same problems in a lot of the same ways. And things like access modifiers still behave exactly as if I was using composition. All right, so I did something illegal, but I do have a get name function that is public. Okay, so now when I made a chicken, right, the animal constructor was called first, and then the chicken constructor was called second. And this is similar to composition. When I had a student that contained an address, the address was constructed first, followed by the student. And then on the destructor side, it happened in the opposite order. Okay, so that's what we have so far. And we have a print function now that sort of prints the animal part using still, observing encapsulation of the animal. I don't access the private members. I just call the public function, and then I add my own behavior to it. Questions so far? All right, we have one more problem, and that is, how do I initialize these member variables, right? So there were some tricks that we could use that were less efficient when we used composition. Those tricks are no longer available to us. But we do have the trick that worked, or the one thing that worked all of the time, which was using the member initializer list. But now, instead of a member initializer list, it's called the base class initializer list. But it's the same way. So how do I solve this? I solve this the same way I solve it with composition. I want to grab the animal constructor before my chicken constructor is called, and I want to give it those parameters. And how I do that is just with the name of the class. So name, age, and lifespan I can pass in. And then if I wanted to, I could do, I could also initialize my egg count member variable there instead of down here. And then, yeah, well, that goes on. Quite long, I suppose. Let's bring this down here. So yeah, I use a member. This is so ugly. All right, so how do I initialize the animal part of my chicken? Well, I use a base class initializer. And it's basically the same solution as I have when I'm using composition, right? So now my chickie, well, let's give chickie some actual parameters. So now I have a life or an age of 5, a lifespan of 10, and an egg count of 5. And it's starting to probably file a bug report about that or something. It is very easy to reproduce. Of course, I filed many bug reports with Microsoft, and it's, I guess they're busy guys because they don't get around to it. All right. I did mean EC. Thank you very much, compiler. All right. Okay, so now my chicken is completely constructed. So the animal constructor gets called, and in inheritance, every constructor along your class hierarchy always gets called, right? So the base class is definitely going to get called. If I here I'm using the base class initializer syntax in order to pass it some parameters before the constructor is called, the same way as I would do with composition. And the same thing with composition is, well, here I had all default arguments, right? So the fact that I wasn't actually calling the animal constructor didn't matter. The animal constructor was getting called with default arguments. But if I didn't have all default arguments, then I would have to do this, right? Otherwise, it would not compile, right? Actually, if I take that out, yeah, so no matching function for a call to the basically a default constructor for animal. Okay. All right, questions? Okay, so yeah, it's inheritance, but it's useful to think about it as composition, except now we have a new well, it was an old access modifier, but now it has an actual use in that we can declare some of my members of my base class visible to my derived class. Right, so public and protected members can be accessed by the derived class, as we've seen. So lifespan and, well, the print function. Private base class members can only be accessed through private or protected members, or using, if you declare it a friend, but never directly. It follows the same rules as composition. And like composition, if I want to sort of access some of the behavior of this animal subpart, well, I can do it. But instead of, I don't have a variable, I just have a reference to the class now. So member access, well, so my derived class, I cannot access the private members of a base class. They become invisible. But the protected members of my base class stay protected in my derived class. And the public members of my base class stay public in the derived class. And then on top of that, I can, of course, declare a bunch of new members and say that they're either private or protected or public. Of course, if I go deeper into my class hierarchy and maybe I have a second or another ancestor, let's say, another child of a child, well then this private thing that became invisible in my derived class stays invisible in my derived class, in my grandchild. It still exists, right? I can still access it through the public members of my base class. Protected members stay protected. Public members are still public, right? They stay public. But now if I look at the members that I declared in my child class, in the grandchild class, they follow the same set of rules, right? So private becomes invisible to the grandchild, protected stays protected, public stays public, and then of course I can declare a whole bunch of new stuff, and we can go on. I don't know if there's a limit to how deep your hierarchies can go. I mean, in a practical sense, you don't want to go too deep, but yeah, you just keep going. Those are the rules that you would follow. So using inherited members, public and protected members, I can access directly by name. The private members, I still have to observe encapsulation and only access them through public or protected member functions, such as the constructor or any functions that are allowed. The order of construction, it follows, well, if I say had a Mazda class and the Mazda inherited from the car class and the car class inherited from the vehicle class, when I construct a Mazda, well, the first constructor that gets called is the vehicle. Whether or not, if I don't supply any arguments, it's going to look for a default constructor. If there's no default constructor, then it will fail, it won't compile. So this constructor is always called. Second is the car constructor, and then third is the Mazda constructor. And when they're destroyed, well, that actually happens in the opposite order. So now the Mazda part is destroyed first, the car part is destroyed second, and the vehicle part is destroyed last. Again, that follows the same rules as composition. All right. Well, speaking of composition, what happens when we mix the two things up? All right, so now maybe I have an inheritance hierarchy, a very short one in this case, but maybe I also have some member variables that are different classes that also need to be constructed and destroyed. So in this case, here, let's draw a little primitive UML. So at my base, I have an animal class, and the animal class chicken inherits from animal. And then I'm going to include an egg class. But egg class is not part of the inheritance hierarchy. What it is it's going to be stored in the chicken. Right? So the chicken is going to contain the egg is going to be contained by the chicken, and chicken inherits from animal. So this is roughly what our sort of class organization looks like. So yeah, same old animal class. Well, I got an extra getter in there now, but my chicken class still inherits from animal, still has the same members, still does everything basically the same. So let's make our chicken Stanley and then print out Stanley and then take it from there. Okay, so well, animal gets constructed first and then the chicken, so no surprises. I print out my chicken and then the chicken part gets destroyed and then the animal part gets destroyed. Great. Well, now I'm going to add this egg class. This egg class simply has a string as a member, and the string is a size, I guess, for the egg, or a descriptor, or whatever. All right, so here's my egg class. Size gets initialized, so we're all ready to go. We're just going to statically allocate an egg inside the chicken, and then let's add it to the print that can produce some egg count. Is it a get size or just size? Get size. The autocomplete does not, it's not really working very well. All right, so that should add a little bit of spice to our chicken. Okay, so now what happens? Well, the animal part gets constructed first, and then the chicken part gets constructed. But the chicken part consists of now two parts, the egg and the chicken, and so the egg is going to get constructed before the chicken part. And then when we are, and then I'm a chicken that can produce 10 mini eggs daily. And then when we're destroying things, things get destroyed in the opposite order. So chicken was constructed last, it's destroyed first. Then my contained egg gets destroyed, and then we move on to the animal part, and it gets destroyed. And if animal had some member variables that output a message, it would be the same thing, right? So the contained part gets constructed first, followed by the container, and the base classes all get constructed before the derived classes. And yeah, destructors are the reverse order, essentially. Okay, so yes, this is, I've rearranged the order that we took these in. So this is what we already talked about, where I can initialize the base class using the base class initializer syntax. And yeah, So here's the syntax. It's basically exactly the same as the member initializer syntax. And it does basically the same function, right? My coyote has an animal part. We want to construct the animal part, and so we want to pass in arguments to that constructor, and this is how we do it. All right. So, questions so far? All right, a lot of details about inheritance. Let's talk about functions. Right, so the base class inherits everything from the derived class inherits everything from the base class, including functions. So here's our animal class. We've added a little bit to it, right? Now we have these two forage functions, which just basically means the animal is going to eat either for some number of minutes or for some number of hours. And you know, a little bit about C++ is that this is called function overloading, right? And what that means is that my two functions have the same name, but I just have different parameters, right? So the compiler can tell them apart by the parameters. So you're not allowed to do this in C, but in C++, it's fine to have two functions with the same name. The compiler will tell them apart. So now my chicken class, well, I don't have to add those functions to my chicken class. I inherit them automatically. So when I make an animal Al and a chicken Chicky, I can print them both out, and then I can have Al forage, and then let's have the chicken. Chicken's very hungry, so it's going to forage for 30 minutes, and then also another half hour after that. Okay, so yeah, so these are animal functions. Oops. So yeah, when I print them out, I have the animal Al, and then I have the chicken, who is also an animal. Al forages for 20 minutes, the chicken forages for 30 minutes, and then the chicken forages for half an hour. All right, and that didn't require anything other than I inherit from animal, so I get to use these animal functions. All right, so let's look at something funny happens though, however. If I want to add some foraging behavior to my chicken, let's say I wanted to do something like this. I'm going to add a forage function. Are these const? Yeah, they are const. Make this const as well. Okay, and then in my chicken class, we're going to implement that. Forages for food type. Okay. So now I've overloaded this function again, but again, I have a different parameter, so that's technically allowed. I go back here. Okay, yeah. All right, well, let's compile that and run it. Well, actually, let's add something here. Chicky. Chicken's going to forage for worms. Oh, well, now I have problems. Where I had no problems before, and it's not even with the forage function that I made. It's actually with the forage function that I inherited, right? And yeah, of course, this is a little weird. I says, cannot convert an int to a string. In other words, I called forage here, and it thought I meant this forage, even though I meant the animal forage. So that wasn't a problem before, but now that I've added this new forage function, it is a problem. I'm not sure exactly why that is, but for now, in the sense of, yeah, well, let's see the solution and then talk about the philosophy behind this decision. Okay, so if I comment out the animal forage calls and just stick with the chicken function call, then it's fine. It runs, the animal's at feeding time, owl forages for 20 minutes, and the chicken forages for worms. But I seem to have lost some functionality here. Thing is, I didn't lose it. It's still accessible to me, but now not directly for some reason. And again, I'm not really sure the reasoning behind this decision. But if I want to use this forage function, I have to tell the compiler, like, don't look in my class. Look in the animal class. Right? So I'm going to use the scope resolution operator. It's a little weird after the dot, but oops, no, that's not what I want to do. That is the chicken one. All right, so now I cannot call these directly anymore. But what I can do is tell the compiler, like, look, this is not a chicken forage function, it's an animal forage function, so please go look in my base class. And then, well, then our chicken can eat all at once. It can forage for 30 minutes, and then it can forage for another half an hour, and then it can forage for worms. Right? So a little weird, I'm not sure. Again, I'm not sure the design decision or what went into this decision, where if you overload a function in your derived class, suddenly the base class ones are invisible. Yeah, I don't know. Could give it some thought. But off the top of my head, I do not know why they would do that, or what advantage or disadvantage it would incur. Questions? Okay. All right, so yes, this gives us some sort of strange behavior, or at least I would find it strange. That would be a bug, honestly, if I wasn't familiar with C++, that would keep me up like all night trying to figure out what is going on. So yeah, if I redefine a base class function in my derived class, right, if I overload it, then the base class functions are now hidden. I can still access them using the scope resolution operator, but all right. Okay, so thus far we've talked about public inheritance, right? So public inheritance is the way we typically think of inheritance. It's the is-a relationship. C++ also has private or protected inheritance. That does not give us the is-a relationship, and we'll talk about why. I still inherit all members, but the accessibility of those members changes, right? Basically, everything I inherit privately becomes now private. And if I use protected inheritance, then everything becomes protected. That's the most access. I could still have private access. This is often used or sometimes used. Basically, private inheritance is sometimes used as a substitute for composition and delegation, although looking at the model that we're using, I'm not entirely certain that that would save you anything at all. But if we look at sort of the access that we get with public inheritance, well, this is what we get. Our derived class, you know, the private stuff becomes invisible, and everything else kind of stays the same. if I want to now use private inheritance, right? So well, then everything is limited to private, right? So this private thing becomes invisible. That's fine. But my protected and my public members from my base class are now private in my derived class. All right, so maybe big deal, maybe not. That does have some implications, right? And if we go down 2 levels, let's say, and it's 2 levels of private inheritance, well, of course, I get the same effect. Now these private, the things that were protected in public over here become private here, and they become invisible here. And then we basically get the same thing, right? Private becomes invisible, but the protected and the public are turned into private. And if I did protected, it would be similar, but now I'm limited to protected, right? So basically anything that was public becomes protected. And so let's talk about the effect that has on the ISA relationship. So what is the ISA relationship and how do we use it? Well, if I, for instance, have a goose and that goose publicly inherits from animal, then it inherits this speak function, and that speak function is public, which means that I can do something like this, right? I can take an animal handle, I can point it at a goose, and I can call speak on it. And that makes sense because animals can speak and so can geese, right? So they both have this speak behavior. Essentially, everything that is an animal can speak publicly. That's sort of the public interface of my animal class. If I now inherit privately from animal, well, this speak becomes private. And so I'm actually not allowed to access the speak function of a goose, which means that, well, the compiler is not going to let you do this, right? The compiler will fail right here. But even if I change this to goose, well, then the compiler will fail here because speak is private, right? So the effect of using private and protected inheritance is that, well, this ISA relationship is based on behavior and any public member variables, but that's sort of less common. And when I use private and protected inheritance, well, I don't inherit that public behavior, right? So that's where I lose the ISA relationship. Questions? Okay. All right. So yeah, why would we ever do that? That's a very good question. Well, let's look at private inheritance as a solution to this problem. We're actually going to look at 3 solutions, but we want to make a stack class, but we're going to be lazy about it, so we're going to leverage the vector class. The vector class for C++ is basically an array-backed list, very, very common, has lots and lots of functions, right? So if I go to C++ vector, there's going to be a couple that come up. All right. CPP reference and C++.com. These used to both be very good. Now one of them is really sort of a lot of ads. I forget which one though. So let's take a look at this one. CPP reference. So it gives you it's a templated class, which we're going to talk about later. You don't worry about that too much for now. It lists all the member functions, right? So a vector has all of these functions at your disposal. And so you can look them up. And a bunch of operators and things like that. Oh, so we want to use that to make a stack. Well, typically a stack is, I have space somewhere. Well, a stack is, of course, a data structure where we can push things on the top and pop them off the top, right? We talked about it when we talked about the function call stack and stack frames and things like that. So basically a stack, although that seems very simple, right? So push things on the top, pop things off the top. That's actually very, very useful for things like, especially like compilers use stacks and, well, a function call stack. And so that principle is very important, that I can only pop things off the top and I can only add things on the top. It keeps things in an order that is important to us. So we don't want to be able to access things that are not directly on the top of the stack. Right? So that is, we want to make a stack. We're going to use the vector. The vector has too many functions though. But let's take a look at it anyway and see. We're going to look at 3 possible solutions. Using public inheritance, using composition, and then using private inheritance. So we're going to make 3 different stacks. This is the interface that we want, right? We want 3 functions. We want to be able to, it's a stack for ints. We want to be able to push an int onto the top. We want to be able to pop an int off, and we want to be able to query to see if this is empty. So let's take that. Okay. So we're going to implement them right here. We won't go to a .cc file. And being sort of lazy programmers, we don't want to implement these ourselves. We have a vector. A vector is very good at implementing stack operations. So the first thing that we're going to do is we're going to publicly inherit from vector. Public. Now vector, you have to give it a type. So we're storing ints, so we give it the int type. Okay, well, if we look, we want to implement push. Push is going to add something to the back. If we look at the C++ reference, back accesses the last data member. We have a subscript operator that does accesses everything. But what do we have? We have a pushback, adds an element to the end. So push we can implement with the pushback function for our int I. For our vector. So I publicly inherit from vector, which means I should be able to say okay. Good, pop. Well, now I want to remove something from the back and return it. Right, so I have a return value here. So if I look at, again, I have a pushback, I have a pop back. It removes the last element, but that doesn't actually say it here, but the return type is void. So this is not actually exactly what I want. I want to store the back element and then pop it off. But we did have, right, earlier we saw this back, which this actually returns the last element. Yeah, all right, well, this is a little bit, anyway. A little bit above our pay grade for the moment, but it does return the thing that we're looking for. So we're going to say int temp equals back, and then pop back. And return temp. And that should implement our pop. For empty, well, if we look, we don't even need to override this thing because, where is it? Well, trust me when I tell you there is an empty function for the vector class. There it is. Checks whether the container is empty, returns a Boolean, it's a const. Well, that's fine. We're not worried so much about const right now, but so technically we can make this a const as well. In fact, I could just not implement this and it'll work because I inherit the public empty function. but I'm just going to be very explicit about it. I'm going to say return vector int empty, right? So my scope resolution operator for these templated types, I have to include the type here. All right, so now I have a stack that's implemented using the stack 1 that is implemented using public inheritance from the vector. So now I'm going to iterate through a bunch of times and push a bunch of things on my stack. And then I'm going to, while it is not empty, I'm going to pop a bunch of things off the stack and print them. And they should be popped off in the reverse order that I added them. All right, so pushing 0, 2, 4, 6, 10, 12 up to 18. And then when I pop them off, they're popped off in reverse order. And that's looking good. That's looking like a stack. So yeah, we can solve it with public inheritance. We're lazy. We just sort of have our vector do all those things. One potential problem is, well, I can do this. A vector has the subscript operator. And the subscript operator, I can access anything. I don't just access the top of the stack. And this is a public function. So I can do things like I can assign the 5th element to be 200. And so now when I'm popping it off the stack, instead of a 10 here, I have a 200. And that completely ruins my stack, right? This is not going to be a useful stack any longer if somebody can sort of dig into the middle and change one of the values, maybe remove a value or do other funny business that we don't want to allow, right? Stacks are powerful because I only have those limited operations. So that wrecks it. So that's not, okay, well, I can go through, I can actually override that function, and I can stub it out to do nothing. I can do that. But then I have to, of course, well, this is my vector. That's not just the one thing. There's a whole bunch of things that I probably have to do the same thing to now, right? I have to stub these out. That's a lot of work. So I don't want to do that. So although public inheritance solves this particular problem, it doesn't quite do it in a way that is safe. All right, questions? All right, well, let's just use good old composition. I'm actually going to steal all of this. And I will modify it in a second. So composition means, well, I'm just going to have a private member variable. We'll call it vec. That's lurking in the background. And I'm just going to forward those function calls to this, this member. Right? It's private now. So now I don't have public access to these things. So technically here, I basically want to do the same thing. I want to call push back on my vector. Before I had public inheritance, so this was all I needed to do, but now I do this. Right, so now I'm going to sort of forward that call to my member. Also down here, I want to do the same things. And here, instead of the scope resolution operator, I can just do this. Okay, so a few simple changes. And now I have stack 2, which should kind of be okay. Well, let's first of all make sure that it works. So I'm just going to push a bunch of things on and then pop a bunch of things off. Make sure I have that nice stack property. There we go. We got 0 to 18 being pushed on and then popped off in the reverse order. That's fantastic. Of course, when I tried to do this, I get an error. So this is no longer, this is really just a function. It's an operator, but it is just a function in my vector class, and I no longer have access to this function because the public interface of my stack class just includes push, pop, and empty. So yeah, that actually solves our problem completely. It's perfectly fine now. This is a great stack. I only, people can only call these public functions, and these public functions only call the vector functions that I want to have called. So there's no funny business allowed unless I allow it. Yeah, good questions. Okay. Well, let's look at stack 3. Stack 3, I'm going to, again, use inheritance, but now I'm going to use private inheritance. And let's grab all this same stuff. Okay, well, as it turns out, this is all the syntax is still good. It's perfectly good. I have access to the pushback. It's private now in this context, but I'm using it inside the class, so that's not a problem. I have access to pop back and back, and this is actually also a valid call, right? So all the same things I did with the public inheritance, I can do with the private inheritance in terms of forwarding calls from my public functions. Let's make sure that the stack behavior still works. Yep, looks good. I push them on in this order. They come off in reverse order. If I try to do this, I get an error. The error is now that it is inaccessible in this context, right? So this, again, this is a function. So I tried to call basically what is a private function. And it's, so yeah, I'm not allowed. So the last two make good stacks using either composition or inheritance. Which is better, I couldn't tell you, because when you get down to the hardware level, they're doing the same thing, right? In one case, it's private inheritance. In the other case, it's composition. Well, when we look at the structs, they look precisely the same. And I'm guessing the function calls are all very similar. Probably depends. Maybe you get one extra, you follow one extra pointer in one case that you don't follow in the other. But I kind of doubt it. But yeah, questions? All right. So that's typically how private inheritance is used. Protected inheritance, probably not used as much. If you would use it at all, this is actually, I mean, we don't, we play up how great inheritance is, but there is sort of, some advice floating around, like prefer composition over inheritance when you can use composition to solve your problem. And I think that's good because composition is, the problem with inheritance, and it's great in the places that we've, sort of traditionally used it, which is like, well, a couple examples of GUI, like if you use Java Swing or whatever, the FX now, to make GUIs, well, those really map very well to objects. And games, also, it works pretty good, although that's arguable, though there are people who would disagree with that. But like if I'm making a game and I have a game object, I can implement a lot of stuff a lot of logic in the game object, base class, and then I can just inherit from that. And there's a lot of code that I don't have to write, right? I can just modify the things that I want. We'll actually see an example of that coming up. So inheritance works really great in those, but it's really inflexible, right? Inheritance hierarchies are very rigid. I can't change things cannot change who my parent is. Whereas if I use composition, I have options, right? I can, well, here I say vector, but maybe I just say list, and list is an abstract class. Well, now I can, if I don't like my vector, I can replace it with whatever I want, right? So composition is more flexible than inheritance, although inheritance does have its place. All right. 5 minutes left, huh? All right, well, yeah, all right, let's try it. Is there a woo clap today? It doesn't look like I'm going to get to it because we're not going to get through multiple inheritance. If I didn't do the linked list stuff, we probably would have made it. But so beginning of next class, we'll probably have it. But let's talk about multiple inheritance, at least as far as we can. Maybe we'll save the actual coding for next week. But so in C++, we have we can do multiple inheritance, right? And really, this is Java actually. So there's problems with multiple inheritance. Not just we're going to introduce you to the diamond hierarchy problem, but that's, you know, that is a problem. But there's also the problem of sorry. I'm looking at the time, thinking about how deep I can get into these topics. Let's just keep this at a surface level for now. So here's the problem. I have what's called an RV, recreational vehicle, which is if it's parked, it's like a house, and if it's driving, it's a vehicle, right? So I want to have aspects of both of those things. You know, using the inheritance as a solution, right? Well, I have a house class and I have a vehicle class, and I want properties of both those things. I want to inherit from both of those things. Now, a lot of languages don't let you do this, but C++ does. Languages like Java will use an interface instead, right? So you can inherit from, say, house, but then vehicle would have to be an interface, which means I don't implement anything. I just say RV will implement these functions. So you can mimic Java's solution in C++, but C++ is a lot more powerful. That also makes it more complicated. I can just simply inherit from both of these classes. But when I do that, I end up with some problems, right? For example, let's say that you know, I'm at a school and I'm keeping track of my students and my employees. And well, a grad student is a student and also an employee. So, okay, I use multiple inheritance. That's fine. However, student and employee both inherit from the person class. It's the same class. And so now what should happen? Well, that's not entirely clear. And in fact, C++ leaves that up to you. So in this particular example, right, again, if we think of this as composition, that means my student object has a person object contained in it. And my employee object has a person object contained in it. And then if I take those two things and mush them together into a grad student, well, then I end up with two of these person objects, and I end up with two names, right? And so that is called, what is that called? So distinct base class, this is called multiple inclusion base class. Distinct base class is this one, where I inherit from house here and vehicle here, but house and vehicle have nothing in common up the inheritance hierarchy. This is multiple inclusion base class where I inherit from student and employee, and they both inherit from person, and I just leave it that way. The problem with this is, of course, I have two names now. I have a name from my student name, and I have an employee name. And maybe that's fine, maybe I want that. but maybe not. So maybe what I want is to give the compiler a hint. And the hint I'm going to say is like, do this, right? If you ever come into this situation where I inherit from student and employee and they both share a common ancestor, make sure there's only one of those things in my struct, right? So when I look at the memory for this, I will find two names. When I look at memory for this, I will find one name. And so yeah, next class we will talk about all the technical details of doing that. That will appear on your assignment 4. So yeah, that's it for today. Today's Wednesday, yeah. I have office hours tomorrow if anybody needs help with their tutorial 4 or assignment 3, but otherwise have a good weekend. And I'll see you next week.